I'm going to go through the 20 questions of the um, practice test here. Okay, so let's go off. Number one, every collision of molecules results in a reaction taking place. That is definitely false because they have to have the right energy and the right orientation. Because the concentration of reactants increases, a reaction occurs faster. That is true. You get more collisions. For number two, for a reaction with a rate law of this, now this we'll clue in on, when A is tripled, the rate will increase sixfold. No, if it's going to be tripled, it's going to be tripled squared, so that's going to be 9. So it'd be 9 times faster. Okay, so that's a false. The reaction is second order with respect to A. That is true. If it's a little 2 up there, that's second order. When a catalyst is added to a reaction, the delta H of reaction decreases. That is true. Okay. Oh, I'm sorry, that's not true. Okay, we're talking about, here's our potential energy diagram, and here's something like this. Okay, if I put a catalyst in, this gets lowered, the energy hill gets lowered, but where I start and where I finish, that's exactly the same. So it is definitely false. It does not change the delta H of reaction. It does change the activation energy, and it does speed up the reaction. Okay, because a catalyst is not used up in the reaction process. That is true. So we have false, true, and false, true for this one. Number 4, which of the following will increase the rate of the reaction? Okay, aqueous and aqueous. Okay, so we're talking about two solutions here. Increasing the temperature of the reaction, yes, that always speeds up a reaction. Increasing the concentration of B, no, if I can increase the concentration of A, that would do it, but not B. Increasing the volume of water, no, definitely not, because that would dilute the concentration. So 1 only is going to be our answer on that. If we have a particular experiment, the rate of the reaction from W to Z is found to be 3 times 10 to the 2. In a second experiment of the same reaction, the rate was found to be 1.5 times 10 to the 2. So let's kind of notice here, that's 3 and that's 1.5, so it's half as much. So which of the following change could have been made in the second experiment? So what could we do that would slow down the reaction? Okay, a catalyst is added, certainly not, that would speed up the reaction. The initial concentration was changed from 0.1 to 0.05. Okay, that sounds reasonable. If you dilute the concentration of W, then that would slow down the reaction. The initial concentration of Z was changed. Okay, again, if we're going to do products, that's not going to change our rate. And the temperature was changed from 20 to 50. No, if we warmed it up, then it would go faster. So the only good answer there is B. Now for questions 6 and 7, okay, we're looking at this potential energy diagram. So first off, it's saying, what is the value of the delta H formation of the transition state? So remember, said delta H of formations is just saying, how is the energy? What's the energy? And where's the transition state? That's at the top of our peak here. That's the energy barrier. So we're just going to look over here and see it's at -10. And that's our answer. So we're just trying to say, do you know what the parts are? And the delta H of formation says, what is the energy of each of these? So we're just going to read those off the graph. Now number 7, if equal quantities of X and Y are placed in a container, in which direction would the reaction initially proceed more quickly? Okay, so this is that whole concept that if we're going to go forward, we have to have this much energy, the activation energy in the forward direction. If we're going to go in reverse, we have to have this much energy. Okay, so we can see that it's going to be easier to go in the reverse direction than it is going to be in the forward direction. So the reverse would happen more quickly in the beginning if we're starting with equal amounts of those two. So going back to the question, okay, which would be more quickly, the forward reaction, the reverse direction? That looks like the answer. Both would proceed at the same rate. No, it's impossible. It's not possible. No. Okay, so answer B, the reverse reaction would go because it has a smaller activation energy. Now back to question 8. How will the portions shown on the potential energy graph above be affected when a catalyst is added? Well, first let's look at it. When we get a catalyst, that is going to start at the same place, it's going to end at the same place, but in between it's going to be lower. How much lower? That's not really important. So what's that going to do? That is not going to change 2, but it will change 3 and it will change energy 1. Okay, so the activation energies for the forward reaction, that will change. So 1 is going to be smaller, and 2 is going to be the same, and 3 is going to be smaller. So 1 is smaller, so we can knock those off, and 3 is going to be smaller, and part 2 is going to be no change, so this is our answer here. Answer B. Okay, back to here, another picture. The solid line represents the original distribution of kinetic energy in a sample and its threshold energy. Okay, which of the following was or were changed to result in the curve? Okay, so first off, since we can see that this line here, that's our threshold energy, is now back here, that means a catalyst must have been added. Okay, now the other part is here's our curve, okay, but now the curve is here, so that looks like now we have a lower temperature. Since it's more to the left, it's a lower temperature. So the temperature is gone down, and a catalyst has been added. So we are looking for a temperature was decreased and a catalyst was added. There we are. Answer A. Number 10. The rate of the reaction at 20 degrees is 3 times 10 to the minus 5. However, when placed in the presence of platinum, okay, the rate of the reaction was measured to be 1 times 10 to the minus 2. Which of the following is true about the platinum in this reaction? Okay, first off, let's look at this number. 3 times 10 to the minus 5, 1 times 10 to the minus 2, that is a much larger number than 3 times 10 to the minus 5, because remember we're saying this is 0.00003, and this one is just 0.01, so this is much larger. So the reaction is going faster. So platinum is an inhibitor? No, if it was an inhibitor, it would slow things down. The activation energy of the reaction was lower. That's true in the presence of platinum. That sounds good because that's what a catalyst does. The platinum reacts with the reactants and would have less mass at the end of the reaction than at the beginning. No, if it's a catalyst, it is not going to change its reaction, and we can see it's not in the reaction, so catalyst is not a reactant. And the presence of platinum increases the kinetic energy of the reactants. No, it doesn't speed them up at all. Okay, it just allows the particles that are there to be able to get over the energy barrier because it lowers the energy barrier. So the answer is B. For number 11, consider the following reaction. A reaction mixture initially contains 0.04 molar chlorine and excess hydrogen. After 0.5 seconds, the concentration of chlorine is 0.01. What is the rate of appearance of HCl over the same time? Okay, so what's going on? We have information about chlorine and chlorine. Okay, information about chlorine and chlorine, but we're asking about HCl. So we are going to figure out the rate of the chlorine going away, and then we're going to change it to the rate of HCl. And we can see, because since it's a 1-to-2 ratio, the rate of HCl is going to be twice the rate of chlorine. So that's one piece of it. Okay, so rate, okay, that we are, by definition, that's the change in the concentration, in this case chlorine, over the change in time. Okay, so we went from 0.04 to 0.01, so that's a difference of 0.03 moles per liter. And that's happening in 0.5 seconds. So if I do 0.03 divided by 0.05, I'm going to get 0.06. Now that is the rate of my chlorine, but HCl is going to have a rate of change twice that because there's 2 to 1. So I'm looking for 0.12 as my answer. There it is. Answer B. Question 12 and 13. Consider the following reaction mechanism. Okay, we have 3 steps. and fast and slow and fast, and that one's slow. Let's pay attention. Which of the following is an intermediate in the reaction mechanism? Okay, so let's try to put these three together to get the overall. Does anybody cancel? N2O4, N2O4. Nothing else seems to cancel. Yes, it is. NO3 and NO3. Okay. Did anything cancel the other direction? No. So the idea here is both of those are going to be intermediates. So we're looking for an answer of NO3 or an answer of N2O4. So our answer is N2O4. NO3 would have also been a good answer. Which of the following is a possible potential energy graph? Okay, so we have a fast and a slow and a fast step. So we are looking for a hill that is going to small activation energy. The slow one's going to have a large activation energy, and the third one's going to be a small activation energy because it's fast, slow, fast. So we're looking for a small hill, big hill, then a small hill. So here we have a hill. Here's a big hill. Here's a small hill. This looks like a good answer. Small, big, small. Just double check. This is bigger than this one and small. So this is big, small, small. That's no good. Here we have medium, small, and huge. That's no good. Okay, and here we have kind of big, kind of small, kind of small. That's no good. So it has to be small, big, small, and that's answer A. Okay, 14. Consider the following set of experiments conducted for the overall reaction. What's the rate law? And what is A in trial 3? Okay, so we have to figure out that number. So first the rate law. Well, the chemical here is A, so it's going to be rate equals K to the concentration of A, and then we need to figure out what that little number is. So is it 0, 1, 2, or 3? Okay, looking at our data, okay, the initial rate, let's just take these first two here. The concentration of A has gone up 3 times. And when that happens, our rate, so we'll take 9 divided by 3, has also gone up 3 times. So we're basically saying that when the concentration of A, changes by 3, so 3 to the x power is equal to 3. So 3 to what power comes out to be 3 times larger? That must be a 1. So the answer has to be rate is 1. If this was 0, then the rate would have been, the change in rate would have been 1. If this was 2, the rate would have been 3 squared, so it would have been 9 times larger. And if it was 3, it would be 3 cubed, which would be 3 times 3 times 3, would be 27 times larger. So the fact that it came out 3 times larger, that's all. We don't care about the numbers, we just want to care about how those go in. So what is A in trial 3? Well, we can kind of look at this and say if we go from 3 to 12, okay, that's 4 times larger. Okay, so since we know it's to the first power, if I want my rate to be 4 times larger, then that means my concentration has to be 4 times larger. So instead of being 0.1, we're looking for an answer like 0.4, and there it is, answer B. Now you can also go the long way, calculate K, and just substitute back into the rate law if you want to, but we could logic it out. If it's 3 times larger rate when we multiply the concentration by 3, than if it's 4 times larger rate if we multiply the concentration by 4. Okay, for the following reaction, the rate of the experiments shown were conducted. Which rate law is consistent with the data? Okay, so we have X and Y, and we have 0, 1, 1, 0, 1, 0, 1, 2. Okay, so let's look here. So if we're talking about 1 and 2, we can see what happened is that stays the same. So this is going to help us with the exponent for the Y. If the rate is triple, if the concentration is tripled, we can see that that is 3 times as well. Okay, so we know that the exponent, the order for Y must be 1. 3 and 3 must be 1. So this is not the right answer, and that's not the right answer. Okay, now these two, let's change color. Here, this one is staying constant, so any change must be due to the exponent on x. So we say here this is doubled, and we can see when that's doubled, the rate did not change. So 2 to what power is going to equal 1, a rate of change of 1, so it must be 0. So the first one must be 0. So here's our answer, answer A. 17. Which is the following is a possible equation consistent with the graph? Okay, well, a couple things. X and Y, so which one is the reactant, which one is the product? So the reactant is going to get used up and it's going to go down. So we can say, okay, so this must be Y must be the reactant. So it's going to be Y turning into X. So Y turning into X, so we know that's not the answer, and we know that's not the answer. Now the second part, we can see how much did Y change? Y changed this much, where X only changed this much. So we can say Y is changing, looks like twice as fast as X is, so 2Y changes into X. That's the answer we want, and that looks like answer B. Okay, last few questions. Which of the following is the overall reaction for this step? Okay, overall reaction. So let's put these together. Again, I like to draw a line through the arrows to help me. And I need to cancel out anything that shows up on both sides. So here's 2 CLs and Cl, Cl. And anything else cancel out? Yes, here's an F and here's an F. That cancels out. And nothing else seems to cancel out. So what have I got left? I've got a Cl2 plus F2 turns into 2 ClFs. So I'm looking for Cl2 plus F2 turns into 2 ClFs. It looks like answer B. 19. Consider this reaction. At a particular time, the rate of the appearance of AB2, this one, is 3 times 10 to the minus 2. So what is the rate of disappearance of A? Okay, well, I can see that if I take this rate and divide by 1 and multiply by 2, so since it's 2 to 1, this rate is going to be twice the size of this rate. Now, we're not worried about signs because we're using the words appearance and disappearance. So the rate of A is going to be twice the rate of A2B. So instead of 3 times 10 to the minus 2, I'm looking for 6 times 10 to the minus 2, and that is answer D. Okay, last question in the multiple choice. Consider the following reaction and its rate law. Okay, the rate law is this guy. Okay, so first order with N2 and second order with Cl2. Okay, when N2 is 0.05 and chlorine is 0.05, and they're placed in a container, and the rate of the reaction is X, what is the rate of the reaction when N2 is 0.1 and Cl2 is 0.1? Well, this is kind of a math problem now. So what are we saying? We're saying that N2 is to the first order, and what have we done? For N2, sort things out, 0.05 has changed to 0.1, so we have doubled that concentration. So it's doubled, but it's to the first power. Okay, and then for my chlorine has gone from 0.05 to 0.1. It is also doubled, okay, but this is to the second power. So my new rate, okay, is going to be 2 to the first power, so 2 times 2 to the second power, which is 4. So if this rate is X, then this rate must be 8 times X. So I'm looking for 8 times faster because I can tell from my ratios and my orders of the reaction. And that's the multiple choice section. Okay, I have time. I'm just going to try to continue with the free response section. So here we have our chart. It's going to be a little iffy here. So we want to try to draw the potential energy graph of the uncatalyzed reaction with a solid line. Okay, we're going to try to draw the potential energy of the catalyzed with a dashed line. Okay, so we're looking for clues. What do we know? We know the delta H of formation of B, okay, that's our product, is at negative 90, so we'll put a line right here. And what else do we know? We know that the transition state in the catalyzed is negative 50. Okay, the TS, that's the transition state for the catalyzed reaction, is at negative 50. So I'll put a dot right there. We're going to need that. And what else do we know? We know that the delta H reaction in the reverse direction is positive 20. So we're starting here, we're going to go up by 20. So that means our reactants are here. And the other clue is that our activation energy for the catalyzed reaction is 50. So starting from here, I can go 10, 20, 30, 40, 50. So here's my transition state for the uncatalyzed. That says uncat. Here's transition state for the catalyzed. And here's my initial and final. Okay, so we can start our graph. So I can start here, go all the way up here, and go down to my products. Okay, then I want to do it again for the dotted line for my catalyzed. So start in the same place, but only go to here and end up in the same place. Now I also want to kind of show label the A and B and transition states. Okay, I got my transition states, and we're talking about A turning into B. So here's A and here's B. And I think that that's everything. Oh no, we want to do activation energies. So activation energy in the forward direction is from there to the transition state, but for the catalyzed, it's only here, that tall. For the reverse reaction, okay, we're going to say that it is from the products all the way up to here, and for the catalyzed, it's from the products just to there. Okay, so let's fill in some numbers. So we say the delta H of formation of A, or just look at it in the graph, that's negative 70, and these are all kilojoules per mole. The delta H of formation of the uncatalyzed transition is at negative 20. Again, I'm just reading it here off the graph. And I'm looking down here, the E sub A of the catalyzed reaction, okay, activation, so starting here, going to here, that looks like 20. These are again all kilojoules per mole. The delta H of the reaction, starting from here to there, that's going down by 20, so minus 20. And this is definitely an exothermic reaction. So for the reverse, we know it's endothermic. And what are we doing? So the activation energy for the uncatalyzed. So in the reverse direction. So starting here, we're going to go all the way to here. So that whole thing is 10, 20, 30, 40, 50, 60, 70. And the activation energy for the catalyzed just goes up 10, 20, 30, 40. So I think we fill in everything that we need to get full points. Now, given the following proposed mechanism, write the equation for the overall. Okay, so again, I'm going to draw a line between my arrows, and I want to get rid of anything that is on both sides. So O's go away, looks like NO3 goes away, and that's the only thing that cancels. So what's my overall reaction? It's going to be O3, O3, NO, NO. So 2 O3s plus 2 NOs turns into 2 O2s and 2 NO2s. Okay, identify any intermediates. Okay, so the things that crossed out and then reappear, that I formed them and then used them up, those are intermediates. So my intermediates are O and NO3. Okay, in catalysts there are none. Catalysts would have crossed out upper left, lower right. They would have been used up, they've reformed, there's no catalyst. Okay, draw a possible energy graph for the endothermic reaction. So endothermic means I'm going to start somewhere and end up higher. That gives me the point. Now, I have a fast step, a slow step, and a fast step. Well, fast steps have short activation energies, and slow steps have tall activation energies. So I want a short, tall, short. And so I'm just going to go up and make that short, and make this guy really tall, and then do a short one, and end up here. Now, there'd be a lot of answers that would match this, but I'm looking for a short activation energy, tall activation energy, short activation energy, and that would get me full credit. 22, given the following reaction. Okay, so first off, what is the rate of disappearance of NO? Okay, well, we're talking about the rate of appearance of N2, so we're given this number, and we want this number. So we can see what happens is, because it's a 1-to-2 ratio, whatever the rate of this guy is going to be twice that size. So we're saying for trial 1, the rate is 1.8 times 10 to the minus 4. So I'm going to divide by 1, multiply by 2. So my rate is going to be 3.6 times 10 to the negative 4. Okay, so what happened on this is moles per liter per minute. Okay, so if I had more room, I would say take this rate, and what I've done is I multiplied by 2 and I divide by 1, because for every reaction there's one of those, and every reaction there's two of those, and so that's why I'm going to get my answer. Now officially, if I said what's the rate, I would say it's negative 3.6, but since it says the rate of disappearance, then I can get away with just saying 3.6. Okay, so a rate of a reactant is negative, but it says what's the rate of disappearance, so I can just use the number. So either one would be okay. Write the rate law for this reaction. Okay, so let's do some logic. First off, the rate law is going to be rate equals K, concentration of our reactants, NO, and concentration of H2. And our job is to find these little coefficients up here. I'm about to fill those in a moment. Those are our orders of the reaction. So what's the rate law? So we say, well, here's a situation where that stays the same and this one has tripled. So for my H2, which is going to be this guy, okay, then the concentration went up by 3. Those 3 to some power is equal to, how did this change at the same time? I can use my calculator, but I'm sure I can do this. So 5.4 divided by 1.8, okay, that looks like 4 times, but I'm going to go double check. I'm glad I checked. Okay, that's actually 3 times. So if my concentration went up by 3 and my rate went up by 3, then x must be to the first power. So this is first power right there. Now the second one I can check over here to see, I'm looking for some place where my H2 does not change. So these two sound good. And I have this one and this one. Okay, so what's happening is when this guy, I can see the 0.012 over 0.006, that is 2 times. And what happens is I have 2.16 over 5.4, and that's 2.6 times 10 to the minus 3. So that's really the same thing as 21.6 divided by 5.4. So that's going to be a 4 times difference. So when this goes up double, then this goes up 4 times. So 2 to the x equals 4. So I know that that x must be 2. So I have a 2 up there. So my rate law, kind of messy, is rate equals K times NO2 to the second power. So it's second order with respect to NO, and it's first order with respect to H2. Now I need to find the rate constant and include my units. So I'm just going to go back and solve for K. So K is equal to the rate divided by the concentration of NO to the second power, don't forget that, and the concentration of H2 to the first power. So I'm going to substitute some numbers, and I'll just take trial 1. So the rate is 1.8 times 10 to the negative 4 divided by concentration of NO, which is 0.006 squared, and H2 is 0.001 to the first power, and that all comes out. That's going to come out to 5,000. Just use your calculator. Now what have I got? I've got moles per liter, okay, per second, per minute, over moles per liter, moles per liter, moles per liter cubed. So that's going to end up with moles per liter on the bottom, squared. I'm going to write it over here. Moles per liter. So it's 1 over moles per liter squared minutes on the bottom. Okay, so that's my unit. That's my answer. And I'm running out of time. So the last part here is just going to have to be substitute now that you know this number. Then just go back to your equation, substitute in these two values, and you get an answer of 6.4 times 10 to the negative 4 moles per liter per minute. Okay, good luck.